Hi there, how's it going? Terry Brown, Mechanical Engineering here with another engineering mechanics video. This time we're going to look at a frames and machines type of a problem. So this is the problem that we've got this time. So we're asked to determine the forces exerted on each member of the frame. Okay, so we have frame composed of horizontal member AB here, this member BC at an angle, and we've also got a pulley with a rope going over it and attached to the wall over here. So we can see that the member AB or the component AB is pin connected at A. So we've got a pin support here. The component BC is also pin connected to the wall. And then we've got a pin connection between the two components here. And there's a pin connection or an axle support here between the roller and the component AB. So with these frames and machines problems, often one of the most difficult things to do is to decide what to draw a free body diagram of. When you first did rigid body equilibrium, often the problems that you were given were just one body with some loads, and it was supported at two places, or maybe one place if it was a built-in support. Right, so the choice of what to draw a free body diagram of, there wasn't really any choice. There was just the body that you're given to analyze. Whereas now that we're looking at frames and machines where you've got multiple components connected together, you now need to decide which component to draw the free body diagram of. Right? Whether you draw one on its own, whether you draw the free body diagram of the whole thing, and it will depend on the problem what you do. And there's no hard and fast rule. You can get kind of an idea by looking at what's going on. But if you can't, then don't worry too much. Just start. Choose one of the members to draw a free body diagram of. Usually choose the member that has a force applied to it, because that's your known or a known load acting on it. Because if you draw a free body diagram of BC, for example, then you're not going to be able to solve for anything. You might be able to write some equations, but there's no known input into the free body diagram or the input into the equations for the free body diagram of BC. So the choice here is, all right, do we draw a free body diagram of just AB, or do we draw a free body diagram of the whole thing? And it doesn't really matter. If you happen to make a choice that makes your solution a little bit longer, well, so be it. Better than not starting and not doing anything. In this problem, I'm going to choose to draw a free body diagram of member AB because I've got a force applied here, I've got a pin connection here, and I've got another pin connection here. So I can see that I'm going to be able to solve for some things with my equilibrium equations for my free body diagram here. Starting with a free body diagram of the member AB, looking at this force here, we can see, well, the force doesn't actually get applied directly to this member AB. We've got a pulley in between the force here and that member. So we need to do something about that. All right, so one way to do that is to draw a free body diagram of the pulley first, and then consider what's going on with that. Okay, so if we draw the free body diagram of the pulley on its own, okay, so remember, a free body diagram, the free means it's free of everything that it's connected to. So the center point there, and we've got the force acting downwards from the rope. Okay, and we can put on that and call that T. So in this case, it's 200, but I'm just going to call that T for now. Now, if we consider that there's a rope on the top here pulling to the left, okay, that rope's going to be going over, and there's going to be a tension in the rope at the top. Hopefully you can see that this is going to be acting to the left, but let's stop and think about this in terms of equilibrium. If this is free to rotate, there's no restraining moment here. Okay, free to rotate, negligible friction. So if this is in equilibrium, then we need some of the moments about this point to be equal to 0. Okay, so if this is the radius of the pulley from the center out to this force over here, and we've got the same radius up here, then This force here is tending to rotate clockwise, T times R. This force up here will need to be tending to rotate anti-clockwise, T times the same R, right? So that has to be acting to the left and of magnitude T. Okay, so previously, we just kind of said force in a cable over a pulley is tension is constant. So now we've shown that by considering the moment about the center of the pulley. Now, if we consider vertical equilibrium, some of the forces in the vertical direction equal 0. So therefore, if this force is acting downwards, then we need the force at the axle of the pulley to be acting upwards, and that also must be equal to T. And then the horizontal force at our pin connection there, it must be to the right, equal and opposite to the one here. And that also, of course, must be of magnitude T. So now we need to think about how do we transfer what we've got here over to the beam AB that we're currently analysing. So we've taken off this pulley, or we've imagined that we've taken off the pulley. We now need to replace that pulley with the forces that it exerts on the beam. Okay, so these forces that we have down here are the forces that the beam exerts on the pulley. Now, from Newton's third law, we have an action-reaction pair. Right? So what we put over here on the beam must be equal and opposite to what we have on the pulley. So from here over to here, what we show here must be equal and opposite to what we've got down here on the pulley. So we put that in, 200 newtons acting downwards and 200 newtons acting to the left. Now let's go and look at the reaction at A. So we have a pin connection at A, so we know that we'll have two reactions, vertical and horizontal. They don't have to be vertical and horizontal, but that's convenient for us for doing our calculations. The other way to think about this is that you've got an unknown force at an unknown angle. Right? But normally with these problems, we find the components of the reaction force. All right, so if we look at our forces here, we can just kind of guess or just make an assumption about the sense of these forces, or we can look at our loading and try and work it out. If we imagine that we take moments about point B, for example, we can see this 200 Newton force here is tending to rotate anti-clockwise about B. So therefore, for that to be in equilibrium, these two forces pass through point B, so they're not going to cause a moment. So this force out here must be acting upwards, right, to cause that clockwise moment to counteract the anti-clockwise moment caused by the 200 Newton force. So we can put that in. I've also put in the arrowhead for this force. Right, so I've looked at the other loading. At the moment, I've got the 200 Newton force from the cable via the pulley. So there's a good chance that this force is going to be opposite to that, but don't forget we've got another force that we still need to put in over here that's at some angle. So this may not be correct, right, depending on what magnitude of force we get over here. All right, so let's put some labels on those so that we can use those in our equations of equilibrium. And then over at the connection here, B, right, hopefully from our previous work, you can see that the member BC is a two-force member in equilibrium. So therefore, we know that the forces at B and C must be equal and opposite and collinear. Okay, so acting along the line BC. Right, so therefore, we know the force at B must be acting along that line B to C. So we put that in, and then we put our force in there. Right, how do I know it's acting upwards to the right and not downwards to the left? Right, if I go back over here and imagine that I take moments about point A, this force, this 200 Newton force, will tend to cause this beam to rotate clockwise about point A. So therefore we need a force over here to counteract that and tend to cause it to rotate anti-clockwise. Right? So therefore this force must be acting upwards and to the right. Just noting there in my solution that BC is a two-force member in equilibrium, which justifies how I can draw the direction of this force. And if we put in that angle, call it theta, and just do some trigonometry, we can work out that angle. So opposite tan theta equals opposite over adjacent. So just inverting that, theta equals inverse tan of opposite over adjacent. So this angle here, opposite is 2, adjacent is 1.5. For those of you who are familiar with the 3, 4, 5 triangle, you can see that this is 2 times 1.5 is 3, 2 times 2 is 4, so this is a 3, 4, 5 ratio. Okay, so you could use that as well. But we'll just use the angles for this time. So if you take moments about point A, so usually in an equilibrium problem, we'll start with taking moments about a certain point, because that will generally enable us to find one of our unknowns straight away, assuming we choose the right point here. And the point to choose is a point where 2 of our unknowns pass through, right? Because that removes them from the moment equation. Okay, so the moment of RA y through point A is 0, the moment of RAX through point A is 0. So that just leaves us with RBC as an unknown. And don't forget, it's important that you indicate down here where you're taking moments about, and also what you're considering to be the positive sense for the moments. Starting with the 200 Newton force acting downwards here, that's at a perpendicular distance from A of 2, tending to rotate clockwise, so that will be a negative moment. So we've got a negative at the front. And then we have RBC sine theta. Okay, so we need the vertical component of this force. So that will be the opposite to this angle theta here, and the perpendicular distance is 4. So RBC sine theta times 4, and it tends to rotate anti-clockwise around point A, so positive. Nothing else causing a moment, so that's all equal to 0. So we can rearrange that, put it into our calculators, and get RBC equals 125 newtons. All right, then we can go ahead and use our force equations of equilibrium. So I'm doing some of the forces in the horizontal direction equals 0. And we have RAX over here in the positive direction, minus 200, plus the horizontal component of RBC. So the horizontal component here is the adjacent to the angle. So that will be cos theta. Right, substitute RBC into here from what we calculated before, rearrange and put it into your calculator and get RAX equals 125 newtons. Now if we do some of the forces in the vertical direction equals 0, right, we have RAY in the positive direction minus the 200 Newton force here, plus the vertical component of RBC. Substitute RBC from before and we can calculate RAY equals 100 newtons. Right, so they're all the forces that act on the member AB. Now let's look at member BC. Drawing a free body diagram now of the link BC. Right, because it's a two-force member in equilibrium, we know that the forces acting on this member must be along the lines joining B to C. Now, important thing to note is that it doesn't matter what shape this link is. Right? This link doesn't have to be straight. We could have, for example, a link that goes this shape. Doesn't matter. Or it could be a curved member like this. Right? Doesn't matter what the shape of the link is. The important point is the fact that there's only 2 locations where forces are generated, assuming that the weight of the component is negligible. The lines of action of the force must be along the line joining those 2 points. Now, when we look at the force acting on our link over here, again, we have an action-reaction pair. So from Newton's third law, the force at B on this member must be equal and opposite to the force over on the member or the link BC. right, because Newton, to obey Newton's third law. So therefore, this must be acting down to the left. So it's very important that you get used to doing this and making sure that you obey Newton's third law when you draw free body diagrams of components that were originally connected, and you've imagine that we've disconnected them in order to draw the free body diagrams. You must show these as equal and opposite. And then the force over here at C must, of course, be equal and opposite to that. And so we calculated RBC over here on the previous page was 125, so this must be 125 as well. All right, so just going back to the force on member AB, if we want to find the resultant force, which is what we'll need to do if we're going to determine the size of the pins, for example, that we need to put in this connection, then we'll need to know the resultant force, so just square root of the sum of the squares. Applying Pythagoras theorem, we get 160 newtons for that resultant force. So just noting now our final answers at the end. For RA, we had 160 newtons, and RBC, we had 125 newtons. Okay, so that's the end of the problem. That's a fairly simple frames and machines problem, but it goes through many of the basics and the fundamentals that you need to get right in order to do more difficult and more complicated frames and machines problems where there are many more members connected to each other. Okay, so I hope that was helpful and hopefully even somewhat interesting, but we'll get on to more interesting problems in later videos. All right, thanks for hanging around, and I'll catch you in the next video. Bye for now.